Okay, hi everyone. Today we have Krishna Mohan Parattu from IIT Madras. He will tell us about quantum evolution of cosmological perturbations, single and two-phase inflation. Krishna did his PhD from IOCA with Professor Padma Naval, and he has done postdoctoral stints in IIT Madras, Chile, and Mexico. Now he is in IIT Madras. So today we'll talk about quantum information in cosmology. Krishna.
Okay, thanks a lot, Nirmalya. Uh, yeah, so the topic for my talk today is quantum evolution of cosmological perturbations in single and two-field inflation. This talk is based on a paper that just was recently published in GRG. This is the reference. And it is with Ritulnath Ravindran, who's a postdoc at Institute for Cultivation of Science in Kolkata, and with Professor Sriram Kumar, who's here at IIT Madras, where I'm currently working. Okay, so let me start. Uh, so just a brief introduction, since like Nirmalya said that the audience is sort of mixed and not everyone who's familiar with cosmology. So I'll just try to give a brief introduction of the overall picture before going into the details of the work and the paper. Okay, so how did our universe come to be? So this is a question that has been of interest, of course, to humanity since the early times of history. So almost all civilizations, they have their origin stories, and what is shown here in this picture is the creation of the universe in Mayan history. And like over them, the stories were of course simplistic in the sense that over here it just says that some gods came together and created the universe, which is depicted in the center. And of course, then for them, the universe was just Earth. So when they said creation of the universe, it's basically creation of Earth and things that go around it. Right now, of course, we know a lot more about the universe, and we do have some stories about how our universe originated. And that story is represented by this picture, which I'm sure that many of you have seen. So the current picture, the standard picture, is what is known as the standard Big Bang model. So that there was something in the beginning, which people call, for lack of a better word, the Big Bang. And after that, there was a period called inflation, which was a rapid expansion of the universe. And after that, the universe was cooled, matter was produced, and it expanded, and it produced the cosmic microwave background and all the galaxies and other stuff that you see. So that is one picture. Of course, there are everyone does not agree that this is the same picture. There are other ideas out there in the literature. For example, some people believe that there was a universe before which contracted and then expanded to form the current universe. So this is what is known as the big bounce. So there are competing theories, but this is how we are trying to understand the universe right now. At least for this talk, I will not tackle such big questions. I'll tackle a slightly more restricted, more limited question. The question of assuming that you have a universe that came into being, then in that universe, where did all these galaxies? So if you look out into the space, so there are all these galaxies that are there, galaxies which form clusters and superclusters. So where did all these galaxies come from? So this question, if you go back again in history and see what did early civilizations say about this, then they did not have many stories about this, basically because at that time, there were not so many galaxies that you could see out there. You could basically see the Milky Way, and they did not know the Milky Way was just one of many galaxies that were out there. Still, at least for the Milky Way, there were still stories. For example, this is a native Indian story of the creation of the Milky Way. So the story goes somewhat like this. So it said that the villagers, they used to keep their food outside the village. And so every night, a dog, a cosmic dog, it used to come down from the sky and steal some food and run away. So one day, the villagers, they just hid in the bushes around. And when the dog came down, they scared it banging on drums. And the dog, while it was running away scared, it dropped some food on its way across the sky, and that is how the Milky Way was formed. So now, of course, we know with the advent of large-scale surveys and all that there are many more galaxies. For example, this is the picture that you get from the slow and digital sky survey, and that is the SDSS map. From this SDSS map, it basically maps millions of galaxies. So there are about 1 million galaxies that the SDSS maps. So there are a lot more galaxies, and of course, for this, the structure that you see out here, you need a different story. Okay. So for this, the story again comes back to the picture that we saw earlier. So the picture that you have. So over here, in the beginning, if you can see near where inflation happens, there is a mention of quantum fluctuations. Okay. So the picture is that while inflation happened, you needed to have a separate kind of matter, a very exotic matter for inflation to happen. And that matter field, it of course had quantum fluctuations because it was a quantum field. So the picture is that these quantum fluctuations, there were later, because of the expanding universe due to inflation, so these quantum fluctuations, they were stretched out. And when they were stretched out, there were inhomogeneities in the density of the universe that were created. And these, as the universe evolved, they were the ones which went on to form the inhomogeneities that you see in the CMB, and which later grew to form all the galaxies and planets, etc., that you see. Uh, Before going into a little bit more details about how that came about, let me talk a little bit about CMB. So cosmic microwave background, that all of you know, that you can uh, see all around, you can see in all directions the cosmic microwave background that exists. It is the most perfect black body that we humans know. It has a very uniform temperature of 2.725 K, and the Erebus are supposed to be so small that they'll be smaller than the width line. It is the most perfect black body that you have around. So once you have this CMB, then there is the question of how the CMB came to have such a uniform temperature, because generally when you have something that has a uniform temperature, that is due to some interactions which lead to thermal equilibrium. Now, if you just here at the center at Earth and you're looking all around and you're detecting cosmic microwave background coming from various directions, and then if you ask yourself that suppose inflation was not there, only the rest of the evolution of the universe, then what is the patch of the sky which would have attained thermal equilibrium starting from where you imagine the Big Bang had happened? So if you calculate the size of that patch, so it turns out that it will have a radius of approximately only 1 degree in the sky. Okay, it will have a radius of only 1 degree, and so something that is within that kind of a patch, about 1 degree, 2 degree patch, that you can expect to have come to equilibrium due to purely thermal processes. Okay, so this is roughly the size of how traveled starting from Big Bang if inflation had not happened. Okay, so of course, if something is so far away that light could not reach from one point to the other point, there would be no interaction. You would not expect there to be any thermal equilibrium. Okay, so this is like a very small size, 1 degree. So 1 degree, the moon is supposed to sustain like half a degree in the night sky. So 1 degree is just like two moons out there, you know. So only such a small patch in the sky, you would expect it to have come to thermal equilibrium. But of course, from our observations using the CMB satellites, we know that CMB, no matter which direction you look at, the CMB always to have the same temperature. So how did that happen? Because according to this picture, if the horizon size was just 1 degree, you would have expected like different patches in different directions with different temperatures. So that is why you need some mechanism to increase this horizon size so that it is at least as large as the sky that we see today. And that is what inflation does. So what inflation does is that it is accelerated expansion in the very early universe, where in that particular time, the universe expanded exponentially. Okay, so there was an accelerated expansion during this time. So this graph represents the size of the universe versus time. So there was this exponential expansion in the early times, and because of this, like patches which were very close together, because of this exponential expansion, they were flung far apart in the sky. Okay, so without inflation, if you start from here and if you go back, then you would say that many of the patches that we see in sky today, they couldn't have communicated even with light signals. But just because of inflation, it is possible that they could have communicated and come to some sort of thermal equilibrium. Okay, so that is why inflation is necessary. And this problem that without inflation you have only this much patch of the sky which could have come into thermal equilibrium, that is known as a horizon problem. And inflation was proposed as a solution to this horizon problem. Okay, it's widely accepted. It's the most standard theory that we have right now. Then there is a bonus from this story. The bonus from this story is that inflation also provides a quantum theory for the cosmic structure for all the galaxies and these fluctuations in the CMB that you see. It provides an origin for that. So how does that come about? So it turns out that in order to have inflation, as I said, you need some sort of exotic matter in the early universe. And the simplest kind of matter that can produce inflation is just a scalar field. This scalar field is called inflaton. And just a scalar field with a potential, it is able to produce inflation. Uh, just yeah, just explaining. So a scalar field is something that requires just a single number at every point in space-time in order to describe it. If you want to compare with the electromagnetic field, which is a vector, it requires 4 numbers per space-time point. The only fundamental scalar that we know right now is the Higgs field. So the Higgs is a scalar, that is the one fundamental scalar that we know. People have tried producing inflation with the Higgs field, but at least as far as I know, it doesn't work. I mean, it doesn't work very well. So probably there was some other field in the early universe which caused inflation. And so how does this lead to these inhomogeneous that I was talking about? So the picture is something like this. So the scalar field, it evolves on top of some potential. Okay, so the dynamics is basically like that of a ball rolling down a hill. Okay, so what happens is when the potential dominates over the kinetic energy, that is when inflation takes place. So the inflaton, it starts somewhere over here and it starts rolling. It's rolling slowly. And once it comes over, it starts rolling faster. And once the kinetic energy dominates over the potential energy, inflation ends. That is the picture. So the inflation ends somewhere over here. Now, since this inflaton, it's a quantum field, what happens is there will be quantum fluctuations. And because of the quantum fluctuations, so the point at which the inflaton crosses this point, this end point, it will be different at different regions in space-time. Okay, so different regions in space-time, the inflation will end at slightly different times. And because of this, you'll get different densities at different points. So that is how you produce an initial inhomogeneous distribution of density. Then, of course, once you have an initial inhomogeneous distribution, as the universe evolves, then there will be other processes and matter will clump, etc., and you'll get structure. So, so that will happen. Those are processes that are understood. Now, this particular process of origin of cosmic structure, it was proposed soon after introduction of inflation. So inflation was introduced in 1880, and soon after, three different groups from three different parts of the world, so Hawking in England, Stravinsky in Russia, and Guth and Weich from the United States, they proposed this theory that it is vacuum fluctuations of the inflaton which will provide seeds for the cosmic structure. And it is not just a random theory because there is some agreement with observations. So suppose you start with the inflaton in its ground state, then the fluctuations at the end of the inflation follow a Gaussian distribution. And they are also nearly scale invariant. What this means is that if you go to Fourier space and look at the power at various scales defined suitably, then you will find that it is independent of scale. Okay, so that is what it predicts, and this matches very well with observations. Okay, so that is why this theory is taken seriously. So once you have this, then you may ask two questions. So why don't astronomers need quantum methods to make sense of observations of the universe? Why does the universe appear largely classical, right? In the sense that if the universe had a quantum origin, but the universe that we see out there, it appears to be largely classical. So what happened to all the quantum features? I mean, where did they go away? Uh, Secondly, once you say that these are of quantum origin, then are there any features in the structure in the universe that will prove that it originated as quantum fluctuations? Okay, if you find some such a signature, then it will be a sort of validation of your original theory that these are of quantum origin. Okay, now let me go a bit through the formalism, the mathematics of cosmological perturbations. So when you have a single field that is driving inflation, the simplest case is to take an action like this. So you have Einstein gravity, which is represented by the second term. Then you have the usual scalar field, the canonical scalar field coupled to it. There is a potential, and the potential is usually taken to be of some form like this, so that there is a flat part where the field can roll slowly, and then there is a part where it rolls fast in inflation x. So for this talk and for this work, we will work in the framework of an FRW metric, which is used for expanding cosmology, that is spatially flat, so that its form is as given. So you have minus dt square representing the time, and you have the spatial part here, and this a square t that is sitting outside the spatial part. So that is the one which tells you that as time goes on, a increases and the universe expands. So once you have this and you have a scalar field that is sitting on top of it, then you can ask what sort of fluctuations you can have in this system. So of course there is a fluctuation in the scalar field delta phi. In addition, there are fluctuations in the metric components. So there will be a fluctuation in the time component and time space and space space. In total, there will be 10 degrees of freedom there. That plus the scalar field, you have 11 degrees of freedom in fluctuations in the system. So this is what we are going to work with. But these 11 degrees of freedom are not independent. So because they'll be related by Einstein equations, and you can remove some redundant degrees using coordinate transformations, etc. So after removing all redundant degrees of freedom, what you will be left with is that we'll have one physical scalar mode, and you will have no vector modes, something that transforms as a vector under three-dimensional coordinate transformations, and you'll have two tensor modes. These tensor modes are basically what you call as gravitational waves. So you'll have two modes there and just one physical scalar mode. For this talk, I'll not talk about the gravitational waves part. I'll just focus on the one physical scalar mode. So you basically have one scalar degree of freedom that is present. And this is represented by something known as Muganow-Sasaki variable Vn. So it is chosen in such a way that it is chosen in such a way that the equations of motion become simplified. Okay. So just understand that when I'm going to talk about cosmological perturbations, in the single field case, you just have one degree of freedom that you have, which is what is going to give rise to fluctuations that later give rise to whatever structure that we see. And that is represented by just a single variable, which is the Muganow-Sasaki variable V. Okay. Now I'll not be working with the real space Muganow-Sasaki variable because it's useful to take a Fourier transform. So once you take a Fourier transform, you get the Fourier components, and then if you decompose the Fourier components into their real and imaginary parts, then it turns out these real and imaginary parts of each Fourier component, they evolve independently, and moreover, the equations that they satisfy are identical. Okay, so you just have to consider any of them, and once you study them, then you can just from the same evolution, you can understand how the whole system is evolving. So we can consider evolution of, say, real part of some Fourier mode with wave number k, which I'll represent by the variable vk, and the corresponding momentum is what is called pk. Okay? And so the classical action for this takes the form that is given here. So there is the first term and the second term. So this together, it is just the equation for a harmonic oscillator. Right? It's just an action for a harmonic oscillator. Only thing is the quotient of vk square that you see over here, it's time dependent. Okay. So the first two terms together, they are just like a time dependent harmonic oscillator. I should just note that by vk prime here, I essentially mean a time derivative. For people who are aware of this, it's a time derivative with a conformal time derivative with respect to the conformal time. The last term here, that is an extra term that comes in. As far as dynamics is concerned, it doesn't contribute because you can eliminate it by a total derivative with some modification in the this middle term. So effectively, the dynamics of the system is like that of a time-dependent harmonic oscillator. Okay, so that is the classical action. Now we want to quantize the system. So in order to quantize the system, what we do is we first construct the classical Hamiltonian. So this is what you see here, the classical Hamiltonian. Here I have reintroduced the integral over d cube k. Just to remind you that when I was talking here, I was just talking about 1k, while in the system, there are, of course, like all the k modes are there, all the Fourier modes are there. So that is why this integral is there, but we can consider each mode independently and study its evolution. Quantizing it, we promote this pk and vk to operators, and we get the quantum Hamiltonian, which is straightforward here. Only the central term, the pk vk, that has been converted to the symmetrized operator. Okay, so this is your quantum Hamiltonian, and using it, you can study the evolution of the system. So you
So,
write down a
Krishna, this
yes.
r by 2 means eta is positive.
No. Actually, the r by 2, that is an integral over d cube k. That r by 2 comes from d cube k.
Okay.
So what happens here is that if you go and do this decomposition to Fourier modes, so the original scalar field is real, okay, and therefore what you get as the Mugnav-Sasaki variable in real space, that is also a real variable. Because of this, all these Fourier components are not really independent. There is a constraint between k and minus k modes. So basically, vk equal to v minus k star. That is the condition that you get, which also happens in usual scalar field theory, right? So that kind of constraint is there. So in order to restrict to independent modes, the integration over d cube k has been restricted to only half the Fourier space. That
Okay, so it's like r by 2 cross r by 2 cross r by 2. All of them are
yes. So this should
like
have
that.
been, I should have put a 3 there probably. So it should have been R3 by 2 then. Okay, I mean three-dimensional Euclidean space by 2. Yeah, so you're right. R cross R would be by 2.
Okay.
Is that fine?
Yeah, yeah.
Okay, so that, yeah, since I did not mention about that constraint, that's why I did not mention that part. But that R by 2 comes just because you restrict to only half the Fourier modes, just to get independent degrees of freedom. Okay, now, so this is the Schrodinger equation. So to find the solution, you can use the Gaussian ansatz. You assume that psi has a Gaussian form as given here, and using that, you can find a solution to this equation. So what is generally done is that in order to provide an initial condition to the system, you go to very early times. So usually at very early times, the middle term that is present here, that will be very, very small. So you can just neglect it. So you just have the other two terms, and that together is just a harmonic oscillator. Okay, harmonic oscillator with frequency k. And so at very early times, what is done is you go and put the system in the ground state of the harmonic oscillator. Okay, and that is what is known as Bunch-Davies initial condition. Okay, you put it in the ground state and then you evolve. Now, what are the things that we are interested in observationally? So, observationally, what we are interested interested in are various correlation functions, and in this case, the expectation value of v and p that will be 0 because we are starting with a Gaussian wave function which is centered on the origin. So those ones will be 0. What you will get as non-zero are the quadratic correlation functions. So if you go to the second order correlation function, these ones will be non-zero. And a useful way to deal with that is that you define some sort of a probability function in phase space. Okay, so you have this v and p, right? This correlation function, these expectation values that you have to take in v and p. So if you have the wave function, of course, you can do it in this case, but it's more useful to talk in terms of a probability function in phase space. Uh, for people who know about this, the one that is usually taken is what is known as the Wigner function, which is just like a wave function in phase space. But for others, just understand that we can represent these statistics of this in terms of some probability distribution that is defined in the PV space, in the momentum position space. Okay, so there is some distribution function that can give you this correlation functions. And once you have that, it is useful to take a cross section of it at some particular height. Okay, so it is just like how you take this full width at half maximum for this Gaussian distribution. So you can just take a cross section at some height. So if the spreads in the momentum and position directions are not equal, in general, you'll out of this cross section. So that ellipse is what is shown here. And at least operationally, in our case, what we are doing is we are going to take this probability distribution function, which is an exponential, and whatever is there in the exponent, we are going to take that and equate it to 1. And that is how we are going to get this ellipse. Okay. So this ellipse represents all that we need to know about this particular Gaussian system. And once you know this, we can calculate all those quadratic correlation functions. Now, in order to parameterize this ellipse, what you need is just the ratio of the major axis and the minor axis, and also its inclination. And so the ratio of the major axis and minor axis is represented in terms of parameter called r. So the major axis is e raised to r and minor axis is e raised to minus r. This r is what is known as the squeezing amplitude. And the angle at which this ellipse is there, this phi angle that you see here, it is known as the squeezing angle. So then quadratic correlation functions, they can be written in terms of the squeezing amplitude and the squeezing angle, and this is the formula that you have. These delta functions here, they come because even though I said that we are going to work mode by mode, if you do it properly in quantum field theory, there will be this delta functions that come about. But of course, if you want, you can put the whole thing in a box and then work with that, and then you wouldn't have these delta functions hanging around. And just compare the commutator in this case. So the commutator, I'm working in the h bar equal to 1 case, and this is the commutator that you have. So this is the system. So we can calculate the quadratic correlation functions, and especially this first one, this vk prime, that is what gives you the power spectrum of this Boganov-Sasaki variable, which you can go and directly relate it with your CMB, your cosmic microwave background. Okay, so that is what is going to give you your cosmic microwave background. Okay, so those are the ingredients that go into the mathematics. And once you have that, now we can talk about the quantum and classical nature of cosmological perturbations. Okay, so the first question is, how do we have a classical universe? So there are many papers written on how these quantum perturbations became classical with the evolution of the universe. So as I already said, the large-scale structure appears to be largely classical, and astronomers are not known to use quantum techniques to analyze their data. And during the 1980s and 1990s, there were many papers written on how these quantum perturbations became classical, starting with Guth himself, Guth and Pi in 1985. Then in the middle of the 90s, 1995 onwards, there was a lot of activity, especially the group of Pulaski, Starobinsky, and Kiefer. They wrote a large number of papers on this topic. A good review to see would be this particular review by Kiefer and Pulaski from 2009. Before I go into what were the conclusions of those papers, I would just like you to note that once you talk about classicality, there is no absolute single criterion of classicality. Okay, because what we are trying to do is we are trying to take a system and trying to determine whether it is classical or quantum. So if you imagine that a classical system is like sort of like a quantum system, it differs from that round sphere in very many ways, just like an elephant differs from the round sphere. So when we are trying to use any particular quantum criteria in order to determine whether a system has become classical, what we are doing is something like what the blind men do when they try to and examine an elephant. We are just taking one part of it and trying to see what happens. So suppose, for example, there is one criteria that we are examining, and that quantum criteria, according to that, we find that the system has become classical. Okay, So that doesn't mean that if you examine with some other criteria, you wouldn't find any quantumness. Okay. For example, if the tail was missing here and this person didn't find a tail, it doesn't mean that it's not an elephant. Maybe it's just an elephant that lost a tail. You could verify that it's an elephant by looking at other criteria. Okay. So that way, just by looking at one criteria, and you wouldn't be able to say that something has become classical. On the other hand, if there is one thing, something that you know is quantum, and if you can prove that that is large, and if you detect it observationally, then definitely you can say that the system is quantum and it's not classical. Okay, so that is the picture. And the second thing that I want you to note is the following, that there is a difference in the way how a person in the lab, a quantum information person, how that person views classicality and how a cosmologist views classicality. So the difference is as follows. Uh, so if you have the phase space, okay, and suppose you have some particle or some harmonic oscillator in that phase space, classically you would expect its evolution to be represented by just a point. So there'll be just a point that is moving around in phase space. Quantum mechanically, it won't be a point, there will be some spread around the point. And if you ask a quantum information person, he or she would say that the most classical state would be one in which the spread between in two directions, p and x direction, they're almost the same. And this is what is known as the coherent state. Okay, in the suitable units, this is what is known as the coherent state. And for a quantum information person, this is the most classical of states. Uh, on the other hand, if you have increased spread in some direction, like for example in q direction here, then that necessarily leads to lowering of the spread in the other direction due to the uncertainty principle. So the state becomes in of this shape. This is what is known as the squeezed state. For a person in the lab, a squeeze state is a very quantum state, because now if you go and measure this q variable, you'll get variance. I mean, your instrument can detect the variation in q. So that is easier to detect than a coherent state. So he would say that this is a squeeze state is far from classical, while a coherent state is close to classical. But once you come to cosmology, we are not trying to compare our system of cosmological perturbations with a classical particle state. We are going to compare it with a classical distribution. In a classical distribution, there is already some spread. So we are not worried about the spread. We are only worried about whether we can reproduce the spread with a classical distribution, something that doesn't have quantum features. For example, if you have a distribution, that probability distribution that is negative at some point, then that wouldn't be classical, right? So the question here is whether we can determine a classical distribution which reproduces our observations. So for a cosmologist, as we will see, a cosmologist will say that something that is highly squeezed, that is what is a more classical state. Okay. Yeah. So as I said, as a conclusion of all those papers from the 90s, and main mechanisms were identified
Sorry,
as the
Krishna,
mechanisms that
sorry, I didn't understand the last statement. So why is it that a cosmologist would say that more squeezed state is classical?
that I'll come to. I mean, that is what I'm going to explain
Oh, okay,
next.
okay.
Okay, at least from this side, I just want you to take away this message that there is a difference in language between quantum information person working in the lab and people in cosmology. Okay, and the difference basically arises from the fact that usually you compare with a classical particle, where in cosmology we compare the quantum state with a classical distribution.
Right. Okay.
Okay, yeah. Uh, okay. So, yeah, so there are two main mechanisms that were identified for making this cosmological perturbations more and more classical. And the first one is called squeezing, and the second one is called decoherence. I had also already mentioned about squeezing. So, what happens is, if you start in the vacuum state at early times, what is known as the Bunch-Davies state, so the spread in pi and pi directions, like the position and momentum, it's almost equal. So you get somewhat like a circle, like your ellipse, the ellipse that I defined earlier, which gives you the variance. It's sort of like a circle. And At early times, if you look at the Hamiltonian, the central term is almost zero. So you only have the other two terms. It's effectively a harmonic oscillator. And at that time, the circle sort of remains a circle. Nothing much happens. As inflation proceeds, this middle term becomes stronger and stronger. Okay, and once it becomes strong enough, what happens is it will start squeezing this particular ellipse, and it'll start elongating it, and it becomes like this very elongated ellipse, and that process is known as squeezing. After inflation ends, there will be still some squeezing, and there will also take place a rotation of this particular ellipse. So that is the process of squeezing. Now, why does this lead to classicality? Uh, so first of all, I'll give you a small, like just something to sort of motivate this. So we were talking about these correlation functions, right? So for example, if you look at this particular correlation function, the VP correlation function, it has some expression in terms of R and phi. When the squeezing is large at the end of inflation, towards the end of inflation, this becomes really, really large. So this one becomes really, really large. Now, I've written it as Vp plus Pv just because these are quantum operators and they don't commute. If they were classical operators, I could have just written them as just Vp. They just add. Now, that quantum nature, the quantum nature that you really have to order these operators, that comes from the commutator, right? The presence of the commutator here. Now, whether you have to take the quantum nature into consideration, you can get a rough estimate of that by comparing the value of this correlation function with the. Now, the commutator is always IH bar. It doesn't change with evolution. It's always IH bar. So once such a correlation becomes really, really large, then what happens is, like, suppose you have some sort of instrument that is tuned to detect some result from this particular correlation function, then it wouldn't be sensitive enough to detect anything, any effects of the commutator. Okay. So that way you can sort of forget about the commutator, and that way you say that the system has become more and more classical. You don't have to worry about the operators, it being actually operators and not classical variables. More rigorously, I can just give you a table from a paper from Martin and Venin in 2016. So what they tried to do is basically what I said before, trying to calculate these correlation functions quantum mechanically, and then trying to reproduce it with a classical distribution. Okay. The first column here is for classical state. Just ignore that for the time being, because anyway, like usually cosmologists are interested in reproducing with a distribution. So what they found is, if you look at the last column that is here, okay, so that is the case when you have a squeezed limit, case in which this correlation function, they are evaluated at the end of inflation when they are in a very squeezed state. Okay, there is okay. So there is also something known as super Hubble. So that is something that I did not explain. It just means that the squeezing, it depends on the scales that you work with. Okay, it only happens for large enough scales, and when a scale becomes smaller than a particular limit, then it may not happen. So you have to look at large enough scales in order to observe squeezing. So if you look at large enough scales which are squeezed, then they found that all these correlation functions, like this first one is just Vk v minus k written in some other form, that is reproduced by a classical distribution. Non-Hermitian 2-point are reproduced. Other Hermitian 2-point correlators are reproduced, and even higher order Hermitian correlators, okay, not non-Hermitian, only higher order Hermitian correlators, that can be nicely reproduced using a classical stochastic distribution once it is squeezed. Okay, so in this sense, there is a connection between squeezing and classicality. That is, if there is large squeezing, then it is easier for us, I mean, it is possible for us to reproduce the results from a classical stochastic distribution. So
Krishna, can you
that
explain
is
again?
about
Sorry,
squeezing.
Krishna, can you explain again what you had said
Yeah.
about the commutation relation earlier?
So
Can
this,
you repeat?
yeah, don't take it. Yeah, so I can explain it again. Don't take it very seriously, because this is just to
Sure, sure.
motivate stuff. So what I'm saying is this, that so I had all these correlation functions, right? Like take one of them, for
Mm-hmm.
example, this one. This is basically the Andy commutator, right?
Mm.
AQPK plus PQVK, and that one, it has this value on the right in terms of the squeezing parameters. Now, at the end of inflation, if these are large enough scales, then this is going to be really, really large.
Mm-hmm.
Okay. Now, once this is really, really large, and you have some sort of an instrument that detects some observational signature of this, maybe fluctuations, CMB or whatever that you're going to detect, then you'll be tuned to some sort of, you'll be tuned to this sort of numbers, right? These large numbers. On the other hand, the the effect of basically the fact that these are operators which do not commute, that is captured by the commutator. Okay.
Right.
and the and the commutator, of course, it is right. So anything that most of the effects of the commutator, I mean, whatever you need for the commutator, like for example, over here, whether you take just VK PK or just VK PK plus PK VK, all those differences, that is captured by something of the order of H bar. Okay. So generically, in late universe, like once you come to late universe, when this becomes large, and if you have instruments that are sensitive to detect these things, you don't expect them to be sensitive to anything that is of the order of H bar.
Okay.
Okay. So that was the basic argument that because of that, the importance of the commutator sort of goes down with squeezing. Okay, that was a motivating argument, but
Okay. Okay. Yeah.
more rigorously, you can see it from this work where they try to reproduce these correlation functions using classical stochastic distributions.
But can we
Okay,
actually see any distribution with PK?
can we actually see any distribution with PK? Uh,
Mm-hmm.
in the case of cosmology, actually, what we do get from observations, if you go back, is out of these three, what you actually get is this V, the first one, the VK
Right.
prime.
Right.
Okay, that is the one that you get. The second and third, as far as I know, people don't know how to measure right now, although it's expected to be really small. This PK prime, not the last one, this PK prime is expected to be really, really small.
Mm-hmm.
So what you get from observations is this VK prime actually from
Mm-hmm.
CMB observations. Although there are, I mean, people do say that if you have other observations that, because CMB is at a particular redshift, right? I mean, it's at a particular time. On the other
Right.
hand, if you have observations that are at different redshifts,
Mm-hmm.
then you'll also get the time evolution of VK.
Right.
So you get a VK, and using that, then you'll get to say about the momentum, like how the momentum is changing,
Right.
etc.
Right.
But we don't have that kind of statistics for any other measurements other than CMB right now.
Right.
So that's why people do say that right now we just have this, the first one.
Mm-hmm.
The second one, we really don't have good measurements from CMB data, etc.
Mm-hmm.
Although they do say that if it becomes too large, like if the spread in momentum becomes too large, then there will be other problems with peaks in CMB and other stuff, etc. Okay,
Okay.
but we don't have like direct measurements of PK prime, for example, or even VK prime, PK prime, that one. Okay, so yeah, so when I'm talking about this particular table, it's not an observational thing. It is a calculation. I mean, they theoretically calculated this from the known quantum theory of inflation, and then compared it with whether you can reproduce it with a classical distribution.
Right.
Okay, it's not an observational thing. What is observationally true is the power spectrum, the k minus v minus k, that it matches very well with whatever we know from CMB.
Okay.
Okay. Okay. So then, yeah. So what is the second mechanism that is at play here? So the second mechanism that is at play here is what is known as decoherence. So by decoherence, what I mean is that in quantum mechanics, you can have superpositions. You can have a cat that is dead and alive, and with due to interactions with the environment, such coherent superpositions are supposed to be eliminated so that you only get these classically expected states of, say, a cat that is alive and a cat that is dead. Okay, so this is the process of quantum decoherence. of course, it is a basis dependent quantity depending on which basis you take. And once you have a basis, which is it is basically determined by what interaction your system has with the environment. And in that basis, mathematically, decoherence corresponds to the reduced density matrix of the system after tracing out the environment getting diagonalized. That is what mathematically happens with decoherence. And decoherence is measured by the entanglement entropy, which is defined by this formula, where rho r is the reduced density matrix of the system. So this decoherence, it is supposed to happen during the evolution of the universe, and because of this, all these coherent superpositions that we don't want, they are supposed to die down, and that is the second process that is supposed to lead to uh, the cosmological perturbations becoming classical. Okay, now I will explain how this happens in some specific models. So the easiest models to work with are what are known as power law models, where the scale factor of the universe, it evolves as a power law. So the most basic case is that of what is known as de Sitter inflation, the case where the Hubble factor remains a constant and the universe is exponentially uh, inflating. Uh, so in that case, and several other power law models, you can see how R evolves. So basically, it evolves and it becomes very large towards the end of inflation. So time runs from left to right, and as it goes on, R evolves, and so everything becomes very highly squeezed at the end of inflation. The large scale, so the large enough scales, they become highly squeezed towards the end of inflation. So that is fine. In power law models, as we expect, things become highly squeezed. If you ask me about the second process, the process of decoherence, then just with the scalar field, you cannot explain it, but you expect that there are other fields in the universe which are present, which come into play even in late universe, even after inflation ends, and that will interact with these perturbations and cause decoherence. Now, another kind of model which has been of interest recently in the literature is something known as ultra-slow roll models. Okay, and now I'm coming to the work that we actually did in our paper. So these ultra-slow roll models, they are of current interest because they have the potential to produce primordial black holes, which is currently considered as a dark matter candidate. Okay, and so people are considering that in the literature right now. There were some indications in the literature that the discussion of classicality would be different in models with an ultra slow roll phase, because you expected that some of the arguments that people had about squeezing and all, it will change in this case. Evolution is different. There was a paper by Deeputer and Dore in 2019 which examined this case in the case of ultra slow roll models. They came to the conclusion that even in this case, there is a high amount of squeezing that is present. So they did not work in terms of the squeezing parameters that we have introduced, but just compared the variance of V and P, etc., and they came to the conclusion that there is high squeezing. So it was interesting to see, to actually evaluate in terms of squeezing parameters and see what happens to classicality in terms of squeezing in this system. Okay, so we studied a particular ultra slow roll model, and we tried to see how this squeezing amplitude grows. And as already expected, it was not just a straight increase. Okay, this ultra slow roll phase, the phase where this ultra slow roll happens, that is in between the gray lines. Okay, yeah, just a little bit about ultra slow roll. So what happens in ultra slow roll is there is the potential that you saw, right? So in the potential, initially there is a very flat part, and that is what is known as the slow roll part. And over there, if you make that potential very flat, that almost exactly flat, that is when you get the ultra slow roll case. Okay, but just the thing is that if you make it very flat, then it doesn't fit within some of the approximations that cosmologists are usually used to making in their calculations. So that is why the dynamics is slightly different. And as you can see, if you look at the evolution of the squeezing parameter here, it is non-trivial. So during the part where there's this ultra slow roll case, it doesn't just increase just like that. There is a part where it actually decreases, or actually decreases. And but once the ultra slow roll ends, then you can see that it again goes to the usual sort of evolution and keeps on increasing towards the end. Okay, So if you have ultra slow roll only for a brief time, in between, and that is what is allowed by observations also, because if you have it for too long, then you have problems with CMB and other cases. So you can only have it for a brief time. If you have it for a brief time, it does affect the evolution of R, but it's not too serious. After that, it seems like the evolution is as usual, and R does indeed become very large towards the end of inflation. So at least by the arguments that we have had, we can say that it does have large squeezing and large classicality by this criteria. Just one thing that I want you to notice is that this particular mode, this red mode, so there is a large increase in squeezing during this ultra slow roll phase. Okay, even more larger increase than outside. That is actually important in terms of this production of primordial black holes, because this R is related to the power spectrum, as we said before. So this large amplification in R, it also leads to a large amplification power spectrum for certain scales. Here the scale is some k equal to 10 raised to 14 in suitable units. So certain scales there is an amplification, and that amplification is power is what is then expected to lead to primordial black holes. Okay, so that phenomena is seen over here. Right. So that was about single field models. Now let me come to two field models. Two field models are of interest because first of all, they provide a richer dynamics than single field models. So suppose you want to keep the CMB the same and you want to produce, say, primordial black holes at other scales, then there are more handles that you can use in a two field model. And secondly, this case you have 2 degrees of freedom because you have an extra field. You have 2 degrees of freedom, a curvature and isocurvature perturbation. They are called curvature and isocurvature perturbation. And generically in models, what happens is these isocurvature perturbations, they are present only during the early universe and then they decay. Therefore, it is natural to consider them as an environment to integrate out. Okay, and you'll only have the curvature perturbation later. So in this particular case, even without other fields being present, you naturally have a mechanism to produce decoherence and have a high entanglement entropy. So the action that we'll consider is of two scalar fields, where the second scalar field has a non-canonical kinetic term. The potential is chosen of this form. So the only coupling comes from this e raised to 2b phi term that is sitting over there. That is what couples phi and chi. The potential is chosen to be this. We consider two cases. First is the case where the two fields are uncoupled. So that is what I'll call the slow roll scenario. So we'll put b1 equal to 0. Both the fields are uncoupled and they evolve almost identically. So it's just the usual single field evolution. The second case is what I'll call the primordial black hole scenario. In this case, you introduce the coupling. So B1 is non-zero. So in this case, what happens is that there is non-trivial interaction between the two fields, and then you'll get non-trivial effects and you have interaction decoherence and other stuff. In this case, the action for the system is what is given here. It's effectively two coupled harmonic oscillators. But now you have 2 degrees of freedom, which are represented by V sigma and Vs. V sigma is what is known as the Bogdanov-Sasaki variable for the curvature perturbation, and Vs is for the isocurvature perturbation, which is what is going to decay out. And the parameter, this psi here, that is what controls the interaction between V sigma and Vs. And this is a plot of that interaction parameter. So you choose it in such a way that it is 0 early on, and then it is turned on only for a small time, and then it decays. Okay, not that you choose it, but if you start with this particular potential, and if you choose these parameters, then you get this chi to be of this form. Okay, and again, you can quantize the system. You have a Schrodinger equation, and it is solved through a Gaussian ansatz. At very early times, these are uncoupled degrees of freedom. So again, you can take the system at very early times to be two harmonic oscillators in their ground state, and that is your Bun-Davis initial condition. So you take that and you evolve. Again, you get all these correlation functions. So what is different here is that because right now it is an interacting system, And if you look at only the sigma sector, there is an extra parameter that comes in, this 2n sigma plus 1, which multiplies all these correlation functions. And that basically represents your entanglement entropy. So this represents the entanglement entropy, and that is the extra parameter that comes into this system. If you again look at squeezing parameter, our first criterion of classicality, so you again see that there is some non-trivial evolution during the time when there is interaction, which is represented by these lines. Again, the middle line here, there is an enhancement of squeezing during this interaction, and that contributes to what I said. It contributes to an enhancement of power spectrum, and which is what we need to produce those primordial black holes at certain scales. Now, the extra thing that we have here is entanglement entropy. So we can look at the evolution of entanglement entropy. There is no entanglement entropy before the interaction starts, and it happens only during the interaction, of course. And as you can see, there is a considerable enhancement of the middle scale. Okay, the middle scale that is present. Just ignore the colors here, just because this figure is taken from a different context, but the dynamics is the same. The red line over here corresponds to the orange line over here. Okay, so that is the one that has the maximum increase in entanglement entropy over here. And if you come back and look at this expression and the power spectrum, which is represented by this b sigma square, so because this 2n sigma plus 1 is sitting out there, an enhancement in entanglement entropy, it will again lead to enhancement of this power. So both these things, this enhancement of squeezing as well as enhancement of entanglement entropy, together conspire to increase the power in this particular scale, this middle scale, and that is what is going to help you get primordial black holes out at those particular scales. Okay. As far as quantum to classical transition is concerned, this is a very good example, because both squeezing, you get high squeezing as well as very high entanglement entropy at the end of inflation in such a case. Okay, so that is about the quantum to classical transition. So the next part is about quantum signatures. I mean, what are the quantum signatures that you might find in cosmic microwave background? So maybe I'll just, yeah, so if there are any questions, I can take them now. And can you let me know like how much time I can take to finish this one?
Yeah, you can take 15 minutes.
Okay.
And if there are no questions, you can take them at the end also.
Okay, all right. So now let me talk about the search for quantum signatures. So during the 2000s, there was interest in proving that the cosmic structure is actually of quantum origin. And this is important because the quantum mechanism that we have just described, that is not the only mechanism that is out there in the literature. There are classical mechanisms using classical processes, thermal distributions, friction, etc. Those are available in the literature. Some references are given here. So because there are alternative models, it becomes important to see whether there is any way you can devise some sort of a measurement that can tell you that things are indeed of quantum origin. So I'll just describe one thread that people followed. So for quantum mechanics, of course, we know that Bell inequalities, they are a quintessential quantum property. So those are the ones which helped verify quantum mechanics is the correct theory that is in existence, rather than some hidden variable classical theory. So it was natural to see whether Bell inequalities can be extended to the cosmological case. So this was first explored in 2005 and 2006 in papers by Campo and Parentani. So they concluded that Bell inequalities can be violated, but decoherence can play a spoil sport. So decoherence can actually suppress this Bell inequality violation. But they also concluded that it's very difficult to verify observationally. Then Maldacena in 2015, he put up a paper where he introduced a rather complicated model that can produce observable Bell violation. So it was a proof of principle model that you can get some sort of Bell violation in some more model, but it was sort of complicated because it had some axions and some extra heavy fields, etc. Then over the past 5-6 years or something, especially Martin, Venin, and collaborators, they have worked extensively on Bell inequality violation. So they first studied it in Fourier space. So in Fourier space, they found that Bell inequalities are indeed violated. Mm, but then in Fourier space, it's not clear what it exactly means, Bell inequality violation, because Bell inequality is generally something that is connected with locality. And locality is more, locality is something that we talk about in real space. And real space is what is more directly connected with observations. So real space violation is more physical, and hence later they studied Bell inequality violation in real space for certain operator which were constructed, and they were for two spatially separated patches. Again, in this case, decoherence played a spoil sport because for the spatially separated patches, when you considered a Bell inequality violation, because of decoherence due to interaction with the other spatial patches, a Bell inequality violation was suppressed. Uh, so over there was no considerable Bell inequality violation. Uh, but there are other type of operators that may be considered because they constructed a particular certain types of operators for Bell inequality violation. That is what they studied, and other type of operators may be studied for Bell inequality violation. And there are also various other Bell type of inequalities like temporal Bell inequalities, Leggett inequalities, etc. So these type of inequalities are still to be studied in the cosmological context. Uh, so from Bell inequality, there is still no considerable signal. Uh, but there was another thing called quantum discord, another criteria from quantum information that people picked up and used in cosmology. So what is quantum discord? So quantum discord is a quantum property that quantifies correlations between different parts of a system. It is more general than entanglement. What I mean is that if you have entanglement in a system, then there will definitely be quantum discord. But there can be systems where there is quantum discord, but there is no entanglement. And secondly, you cannot have quantum discord for a classical system. So quantum discord is again a quantum property. Therefore, even though like people were talking about how the cosmological system has become largely classical because of squeezing and decoherence, people wanted to examine what happens with this quantum discord tool. So it was first used in cosmology by Lim in 2015, and Martin and Menin again in 2015, they did a more extensive analysis to show that this quantity is indeed very large at the end of inflation, which means that the perturbations are in fact in a very quantum state at the end of inflation. Okay, so if you look at quantum discord, so what they considered, Martin and Venin, what they considered was a single field case. So in single field case, they divided the system in Fourier space into plus k and minus k modes, and it is the quantum discord between those two partitions that they studied. So it turned out that the quantum discord in that case is given by this expression in terms of the squeezing parameter. And if you evaluate it, you'll see that for large enough R, it just goes linearly. So for large squeezing, quantum discord is nothing but the squeezing parameter. Okay, so this again comes back to what I was saying earlier with respect to criteria for classicality. Okay, there are various different criteria that exist, and depending on which criteria you pick up and you look, you can say whether you can say that a system is classical or quantum. So we said that squeezing, large squeezing, is something that leads to classicality, that leads to a system being less and less quantum. But if you look at it in terms of quantum discord, then you will see that large squeezing itself gives large quantum discord, and in terms of quantum discord, you would say that this system has large quantum mass. So it depends on how you look at it. So there's no single way to look at it. Depending on which tool you pick up and talk about, and depending on which observations you want to talk about, there are various ways that you can go about doing this. So that is why, I mean, many times when people discuss this in the case of cosmology, they just talk about it as a single thing, a single quantum thing or a single classical thing, but it's not like that. It depends on what tool you use. Uh, so at least quantum discords tells us that there are quantum correlations present in this late universe cosmological perturbations, and therefore it does pay to look for some quantum signature. It's not like all the quantum signatures have been killed by evolution. Okay, so there are still quantum signatures that are left. And what did we do? So we wanted to look at quantum discord for two field models. For two field models, there is a natural division of the system, and that is into curvature and isocurvature modes. Okay, the division into k and minus k modes in the single field case, that is sort of arbitrary, while in this case it's a very natural division. Okay, and you can take the isocurvature of the environment and curvature as the system. So from quantum information literature, when a pure state is divided into two, we found that quantum discord is actually the same as entanglement entropy. So for a pure state, it's the same. Quantum and discord and entanglement entropy are the same, and you can also prove it. And we verified this explicitly by taking a general Gaussian wave function and calculating quantum discord for that case. And it turned out to be the same as what we had as entanglement entropy. And this is again an example of the duality that I was talking about. Maybe I shouldn't call about duality, but saying that depending on how you look at it, you can interpret something as a classical signature or as a quantum signature. So we were saying that coherence is suppressed when you have large entanglement entropy. So that is why large entanglement entropy is a signature of classicality. But if you look at the system in terms of quantum discord, large entanglement entropy also leads to quantum discord. So at least in terms of quantum discord, you would say that the system is highly classical. Highly quantum. Now, this realization that quantum discord is just equal to entanglement entropy, it was useful because while quantum discord is a recent topic in cosmology, entanglement entropy has been around for much longer, and it has been discussed in the case of two-field models much earlier in 2007 and 2014 by these people. And so if you ask me about how quantum discord evolves in the case of two-field models, I just have to give you the same plot that I showed you earlier of the entanglement entropy. So for entanglement entropy, this is how it grows, and that is also the plot of quantum discord. So you can say that at the end of inflation in these two field models, the system is indeed placed in a state which has a very, very high quantum discord. Okay. So if you talk in terms of quantum discord, you would say that the system is highly quantum. If you talk in terms of the squeezing and entanglement entropy, that is squeezing and decoherence parameters that people had used for classicality, you would say that it is highly classical. So it depends on how you look at the system. Okay, so yeah, but these two field models provided with us with a very concrete situation in which to examine these issues and reach concrete results. Okay, so yeah, that was basically the end of my talk. Okay, so thank you all for listening, and more questions are welcome.
Thank you, Krishna, for that excellent talk. So if there are any questions from the audience, please ask. Okay, let me ask something. Why was it that entanglement entropy in decoherence entanglement entropy was considered, large entanglement entropy was considered a sign of classicality? Because I mean, I can understand if a density matrix has like the off diagonal terms to be small, then it looks classical. But just having large entanglement entropy, is it enough to call something classical?
So if you go and look at the system that we had considered, so the system that we had considered was represented by this wave function, right? This Gaussian wave function.
Right.
So in this case, if you calculate the density matrix and then look at the density matrix in this V sigma Vs basis, so the field basis that you have, V sigma Vs basis, and then if you calculate the entanglement entropy, you can show that it is basically related to the ratio of the off diagonal elements and diagonal
Okay, I
elements.
see.
Okay, so that way, yeah, so that way it is related to what you expect.
Uh-huh. And so what is the outlook on basis dependence in these questions?
Yeah, so basis dependence in the case of yeah, you're asking about basis. Okay, um, probably because there was also some papers on how squeezing is basis dependent recently, right? I mean, have you seen those?
No, no. I'm just asking about general, like the general problem of basis dependence and decoherence. And is there any reason to think like there is a preferred basis or something like that?
Yeah, so the basis is usually set by the interactions with the environment, right? I mean, the basis that
Yeah.
is used for here. And over here, as far as I understand, it's the field basis that you have to work in. So you work in the V sigma Vs case, and that is the set basis that you have, and that is what is connected with observations and all. So over here, I don't think you have to worry about other combinations, because this field basis is what is the basis that is most relevant for us, and that is what is supposed to be chosen by interactions.
So that is chosen by observations in some sense.
Well, maybe we should say that that is what is chosen by
Okay.
interactions with other fields, but of course that is what again gives results in our observations also. Uh, so yeah, maybe I shouldn't say that it's chosen by observations. I should say that they're chosen by interactions with other fields, and that is why we work in that particular basis.
Okay. Okay. So if there are no other questions, thanks again, Krishna, for the excellent talk. And I'll
Okay.
stop recording now.